Okay, so this is a kind of schematic of how the vertebrate retina looks like. Vision starts with the photoreceptors. This is the input layer, and the photoreceptors, you probably know that there are two types, cones and rods. In most vertebrate retinas, rods and cones. The rods are the more low light sensitive. I mean, they're more sensitive. They're the ones that we use at low light conditions. The cones are less sensitive to light, but they have a narrow spectral sensitivity, so they provide us with color vision, and we have three types of cones. And one thing to take from this picture, which is still a very simplified picture, is that the retina is a very complex neural network. And broadly speaking, it has these three layers, as I said. So there are the photoreceptors. Photoreceptors project to bipolar cells. Here still the information is transmitted in a graded way, in voltages which are continuous. And then the bipolar cells transmit to the retinal ganglion cells. There are many types of retinal ganglion cells. We'll talk about it in a moment. And this is really the output layer of the retina, because the retinal ganglion cells are the ones that send signals to the brain. So all the brain knows about the visual scene comes from the spikes that the retinal ganglion cells are sending. And in addition to these types of cells, there are additional cells which are not explicitly shown here, which actually some of them are shown here. So there are inhibitory cells in these layers which connect horizontally many of the cells, and there are many types of these inhibitory cells as well. Now, just to give you an idea, I have this picture here which kind of represents how vision looks like in the center of our visual scene. So in the human retina, we have a much denser distribution of photoreceptors in the center in a small region in the center of visual scene called the fovea. This is not common to all retinas, but it's some retinal things. Okay, we have a narrow part of our visual field. We should think about it as about 100 by 100 photoreceptors, where the resolution is very high, and when you go to an optometrist to have an eye test, and you watch the smallest letters that you can still, for which if you can distinguish an E and an F at this eye, you have perfect vision, then the size of the letter when it falls on your fovea relative to the photoreceptor is more or less what you see here. Okay, so you see the letter that you see is about 10 by 10, 5 to 10 by 10, 8 by 8 photoreceptors. But the photoreceptor becomes much less dense in the periphery of our vision. Anyway, here's another picture. And one of the striking features of the design of our retina is that light comes from here, and it goes through the layers of the ganglion cells and the bipolar cells, and it hits the photoreceptors, which are at the back. This is an interesting way that the evolution decided to design the eye, and I think probably the reason is that these cells need a lot of energy, oxygen. So this way here, these cells are close to the blood vessels that provide the oxygen. But I'm not sure that that's the reason. But anyway, that's how it works. And what this means also is that now the light is coming in this way, it's hitting the photoreceptors. These are activating the bipolar cells, these are activating the ganglion cells, and now the ganglion cells need to send their outputs to the brain, and they do this through the optic nerve. And so all these axons collect into one area, and then it needs to go through the layer of the photoreceptor. Okay, so we have blind spot. It's not so difficult. I mean, if you search on the web, you'll find how to, in a small, simple experiment that you can do to observe your blind spot. There's a small region of our visual scene, not at the center. At the center we have our fovea. That's the most important part of our visual scene. But somewhat on the side, the blind spot where we don't is very diverse. It has dozens of cell types. Okay, and this is just now becoming still not mapped completely, but becoming more and more clear from various approaches, both genetic approaches and electron microscopy mapping of the organization of the retina, how many cell types we have. And it turns out that at least in the retina, this is common also to other brain, sometimes to other brain areas, the anatomical cell types that are observed are also correspond to different genetic expressions of to different genetic different expressions of profiles of expressions of various proteins. And so, for example, if you just look at ganglion cells, which is a subset of the types of cells that we have, there are about 20 separate types of ganglion cells, and I think I mentioned it to you also previously from the primate retina. It has become clear that if you look at the receptive fields of these cells, the area that they cover, they kind of overlap. But if you look at one type of cell, each type of cell at the receptive fields, these receptive fields tile very nicely the whole visual scene, covering all everywhere, but with very little overlap between them. So each one of these 20 types is a different channel of information going from the retina to the brain, and we're very far from understanding what is the role of each one of these channels and why do we have so many channels of information. But the most typical kind of receptive field that one observes in a ganglion cell, I've already mentioned it to you, is the center surround receptive field. So, for example, this is an on cell. It's activated by light in the center. It's inhibited by light in some peripheral area around it. And we should really think about the receptive field as a spatio-temporal receptive field. The cells have we can map what is the response in the spatial domain, but also we need to map it in the temporal domain. So this cell might be responsive to an increase of light. So what this temporal receptive field is representing is what is the kind of light profile that would activate a spike, increase the probability of the cell to send a spike right now at this time. We are looking back in time. So a cell would send a spike now, it will be more likely to send a spike right now if it has been activated in the past more or less 30 milliseconds, but in fact it will be better, it will be more likely to fire if it has been though it received less light in this period of about 100 milliseconds before. So this cell is the most kind of situation that is most likely to elicit a spike from the cell is the situation where there's now more light than there was with previously. So the increase of light in the light activates the cell.
When you say typical, does it mean that there are many types of these cells, but with different weights or plus minus?
Yeah, there are plus minus. That's right. But I think many of these cells, there are some cell types which just haven't been characterized.
So how do you define them as different types?
So there's anatomic, genetic. So for example, in the mouse retina, the place where the genetic tools have been the most extensively used is the mouse. And in the mouse retina, once people just started to find markers that allow them to tag particular cells and address them, people realized that these cells have special properties. So for example, there are direction selective cells, that are cells that are selected to something that is moving in a particular direction. Okay? So it's more complicated. I mean, this is the classic, most widely observed kind of receptive field, but there are more complicated types of responses that I'm not going to discuss. In Nerphobia, I think that this is really what these people believe is the kind of receptive field. But this is actually not known. So in the center of the phobia, the most important part of the visual scene, nobody knows what the responses are like, but people do know what are the responses a few degrees from the phobia. Okay, now another striking aspect of the retina is the convergence from a large number of inputs to a smaller number of outputs. So if we look at the array of photoreceptors in our retina, you see that there are about 100 million photoreceptors. And then if we go one layer next to the bipolar cells, there's a reduction by a factor of 10. then if we go to the ganglion cell layer, there's another reduction by a factor of 10. So there's about the photoreceptors themselves generate some limited resolution version of the visual scene, which is infinite dimensional, right? It's a continuous signal. But then from the level of the pixelation of the photoreceptors, there's a reduction in the number of outputs by a factor of 100. Maybe we'll stop now for a break and I'll continue. רוב המדידות שיש מרטינות הן מדידות הרי של אלקטרודות, עושים את הרטינה, סביבות הרעי. ואז הם מודדים את אותם תאים שהאלקטרודות נמצאות, אבל הם לא יודעים בכלל איזה סוג של תא. לכן ברוב המעבדות הם בדרך כלל מראש מחפשים תאים שמבינים משהו על הסביבה שלהם, וזה התאים של זה. מעניין זה שהמעבדה העיקרית שעשתה מיפוי, הסוגיה הראשונה, אני חושב, המעבדה הזאת שיש בערך 20 סוגי תאים, המעבדה של צ'יצ'ילינסקי, סן-דייגו. כן, הוא עבד עם אלקטרוד הרי מאוד מאוד עדין, מאוד מאוד צפוף, שאפשר לו באזור מסוים של רטינה, כל מה שאתם חושבים, לבדוק את כל התאים. ואני כבר לא זוכר איך הם עשו באמת את המיפוי הזה ב-20 תאים. לא פשוט בכלל לעשות את הקלסיפיקציה בצורה כזאת. אבל מאז, ממש בזמן האחרון, הגיעו למסקנות דומות מקולקטומיה. זה בעצם כאן הרצאה של יחידת פנסור, שבה בדיוק אותה מסקנה, שמסתכלים על המפה השטות של המבנה של הסטריטים, של התאים, ואיך הם מקבלים איתותים, והתנועה של התאים, ומגיעים כמה סוג קלסיפיקציה ומגיעים למסקנה הזה. ובכנס שיהיה בשבוע הבא, ידברו גם סבסטיאן סונד, אני לא יודע אם הוא מדבר על הנושא הזה, אני לא ראיתי את הכותרת של ההרצאה שלו, וגם מרקוס מייסטר, שהוא בעצם הראשון שפיתח את הטכניקה של האלקטרוד, הוא מדבר על האלקטרוד, של הרטינה. ואם זה נושאים הספציפיים האלה מעניינים אותך, כדאי מאוד לבוא להרצאות שלהם. גם פה עכשיו, היו לא מעט הרצאות על הרטינה, או על ויז'ן מוקדם.
חבל שלא יודעים יותר.
אבל יודעים יותר מאשר כל מערכת אחרת מחשבים.
כן.
בין X ל-90, בין כאילו... מה אנחנו רוצים...
מה, DX,
כן, זה פשוט יכול לעזור. אבל הלוג של זה עדיין לא משתנה.
זה הבעיה שלי.
זהו.
באמת לא השתנה.
מה?
קראתי זה ירד מאוד קשה.
אבל זה מוזר, מה נשתנה לך?
זה כמה עברתי.
נו,
עבדתי שם. אז ישבתי פה עם החישובים שלי. עשיתי את זה. הלכתי אליה, וחשבתי לשבת פה, אחת הלכתי עוד פעם, ובגלל נורא מפואר לי. לא, היא לא הייתה פה.
אז זה יפעל לך, אנחנו רואים, זה בדיוק כמו שחשבתי, שחררתי עליי, אבל פשוט לא הבנתי מה עשיתי בהתחלה, בהתחלה עשיתי ככה ולשמוע
אני לא הבנתי מה עשית.
כן, בהתחלה לא הבנתי למה לא עשיתי ככה. לא, אבל פה לא זה מאוד קשה.
אתה יודע, הכנסת פרסמה את הרגולציה בעמודים?
היא תמיד לפרסם את זה. שאני נזרח לשלוח אותו?
אין תחמי.
אני מסתכל, אני נזרח אם היא פרסמה.
טוב. Okay, so in our quest to find a time for extra lessons, I'd like to check about Tuesday. For Tuesday we have a class between 12 to 2. How about Tuesday from 2 to 3? No? Tuesday from 11 to 12? Any objections? Okay, no objections. So it's going to be Tuesday. So we'll do one extra hour next week, which is good because then next week we're not missing any hours, but then we'll need to also find one or two other occasions. Okay, so next week I'll send also a notification on the mail. We'll have an extra hour. One thing I want to mention about this statement that in the primate retina there are 20 channels of information. It doesn't mean that they all have the same number of cells. So the receptive fields in some of these can be much wider than in others, and therefore the distribution is not uniform across these different channels. Okay, so we discussed this convergence in the retina from the photoreceptors to the ganglion cells. And now when we look what happens to the information, so now remember the ganglion cells need to send the information through this optic nerve, and it therefore kind of makes sense that maybe it's important for the retina to be economical in the number of outputs that it uses. But then the information reaches the brain, and what we see in the brain is a divergence or expansion. So the route of the information is that it goes first to the lateral geniculate nucleus, and the lateral geniculate nucleus, I don't think anyone understands what it really does, but it's a relay. Okay, so that's the statement. It's a relay. The receptive fields of neurons in this area are very similar to those of the retina, center surround typically. There is some understanding that the LGN can have both the direct inputs, say from the retina, but also other inputs that can modulate its output. But again, the role I don't think is understood. And then from the LGN, the information goes to the primary visual cortex, V1, in the back of our head. And now there's suddenly an expansion by a factor of about 100 from the retina. Okay. So in the number of cells. Now, I mentioned that the receptive fields in the LGN are very similar to those in the retina. If you look at V1, we see something completely different. So the most classically characterized types of receptive field in V1, they're characterized by, I think, first by Hubel and Wiesel, who got the Nobel Prize for their work, are the so-called simple cells. And so this is a receptive field of a simple cell, probably obtained using reverse correlation, which I discussed with you recently. And one very characteristic aspect of receptive fields in V1 is this non-symmetry. They're not radially symmetric around some point. They have this elongated form, so this particular cell is sensitive to stimuli that have a particular orientation, like bars. And this one is inhibited in this region and excited in the surround. Very often it's the opposite. You have a center, which is a line, which is the area of excitation and inhibition. So mathematically, these kinds of receptive fields are modeled as Gabor functions, which are simply some oscillating function, okay, in the direction perpendicular to the bar, and multiplied by some Gaussian that looks like this, okay? These are simple cells. Often these cells are also sensitive to motion in some particular direction. So if you just shine a bar, they won't respond much. But if you move the bar in particular direction, they will fire. There are different spatial frequencies characterizing different cells. There are cells which are called complex cells, which are not just sensitive to this kind of picture, but also to some translations of it. Okay, so it will not be just sensitive to a bar in this particular position, but to bars in any particular direction. So to model such the response of such a cell, we cannot use the simple linear, nonlinear
model that we discussed previously. You have to have a more elaborate model even just to describe what makes this cell fire. And then some of them are color sensitive and so on. We will talk a bit about these receptive fields, how come they emerge later on in the course, or at least some computational explanations for these Gabor-like functions. One other thing, just for completeness, and very briefly, if we look what happens to the visual information after the primary visual cortex, there's a generally accepted distinction between two pathways. One of them, as we believe, is concerned with identification of the content of the image or identification of objects, and this pathway goes from the primary visual cortex to V2, to V4, and to area IT. And as you go from this area to this area to this area, what you observe is that what makes a cell fire is, on one hand, more difficult to even to understand and to describe, but it's what is clear is it becomes more general. So while these cells have a fairly simple form of stimuli that makes them fire, these cells will fire to a more general set of stimuli, and as you go to IT, you find cells that are sensitive to a certain shape, but in various locations, various sizes. So they're somehow more generalizing. The responsive to some feature, but in a more general much more general way than in V1. There's another pathway which is concerned with some understanding of where things are happening in the brain, and this is this pathway from V1 to V3, empty and parietal cortex. Now, I want to go back to information and try to kind of in a very rough manner think about the retina and about how much information is encoded by the retina. So if you want to estimate what is the information rate encoded by our retina, here's a naive kind of simple way to do it. As I mentioned, we have about 100 million photoreceptors, and let's think about the dynamic range of each photoreceptor, meaning the number of different amplitudes that it can discriminate. Perhaps it's 8 bits, I think it's probably more, but even just the fact that when we look at monitors that work with 8 bits look to us reasonably good tells us that this is already a good probably representation for the resolution of our visual system in terms of the number of different amplitudes that we can identify. And so maybe 8 bits.
What do you mean by encoding amplitudes by bits?
So if you have 256 different levels, you would need 8 bits to encode them, right? Of course, we discussed entropy, and we know that that's true if all these levels appear with the same probability. So our estimate here is naive. We're just imagining that all possible, we can discern 256 different amplitudes. If they all appear with the same probability, and we encode, or if we encode them in a naive way by just assigning 8 bits to these 256 possibilities, then we'll need 8 bits, right? And what about the frame rate? So we know that if things appear in a rate of a few tens of hertz, then they already look to us smooth. So our visual system, that's more or less the rate of refresh that we should think about for the visual stimulus. So
you think it's 60 hertz? Right?
Okay, so everything is order of magnitude. So let's not worry about factors of 2. So we multiply all these numbers, and we get 2 times 10 to the 10 bits per second. Okay. Now, how many bits of information are actually sent from the retina to the brain? So this is, of course, difficult to measure because the retina is not sending a stream of bits to the brain. It's sending spikes. Nevertheless, if you're interested, you can look at some kind of rough estimates that have been done recently. And I'm not going to go into a discussion of how this was done, but in this paper, the claim is that the retina is sending 10 million bits per second to the brain, okay, of information. And so you see that there's a large reduction from this number to this number. Okay. Now, how could this be happening? How could it be that the retina manages to convey information which naively is 10 to the 10 bits per second with only 10 to the 7 bits per second? Okay, so there are redundancies. We used this term in the first maybe lesson. There are the redundancies in the retina, in the visual scene, not in the retina. The pixel right here is correlated with a pixel near to it, and there's also redundancy in time, right? And in fact, these redundancies are used extensively also when we encode pictures and movies in a digital form. So, for example, the typical compression ratio from a simple digital format where you encode each pixel independently of the others with, say, 8 bits, and you encode independently in time the value of each pixel, which would require this kind of rate of information. When we encode the same movie using a more sophisticated encoding scheme such as MPEG or other compression algorithms, one obtains a compression ratio of about 100. Depending on the algorithm which is being used. And these algorithms, they're in fact, I think that when people started to develop them, they were very much motivated or inspired by what our visual system is doing. They're using the redundancies in the visual scene in a quite a similar manner, at least in the principles, as our visual system. So you see now, but so you see that in some sense maybe our retina even is a bit better than MPEG in the ratio. Now, the next thing that I want to talk about is light adaptation and perceptual limits in the visual system. The first thing to note, to understand about the visual system, which I kind of ignored so far when I said that maybe our eye can discern 256 levels of light, that's a complete lie. That's absolutely incorrect, because we are able to deal with different levels of light which vary just in our natural environment by many, many orders of magnitude. So the amount of light falling on a retina in full daylight is many orders of magnitude larger than the amount of light falling on a retina in the dark. And our visual system is able to cope with these different situations, but this has to do with very, very significant mechanisms for adaptation which exist in the retina. So this is taken from a paper by Bert Sakmann. It's the same Bert Sakmann who later won the Nobel Prize for developing the patch clamp technique, but this is probably one of his first papers. This shows one of the most basic characteristics of response in the retina, which is that you take the retina and you shine on it for some time light in some intensity. Okay, so you let the retina get used to light in some background intensity, and then you measure the response of one ganglion cell, response being the spikes per second that it's sending, as a function of a spot of light that you shine on its receptive field. But this is after it has been adapted to some certain background. And so each one of these curves correspond to a certain background, and you see that depending on the base, and this is a log plot here. The x-axis is in a log plot. So basically, if you shine light which is stronger by a factor of 10, then the whole response curve of this ganglion cell shifts by a factor of 10. Okay, so it tells us that there's some mechanism of adaptation to the ambient or the general light intensity in the visual scene. But as I'll show you in a moment, the picture is more complicated than that. This is true in some range of light intensities. And so, depending on the general light intensity, the region of light intensity that the retina responds to shifts. Okay. As I mentioned, another very important feature of the retina, the ganglion cell responses, are the central surround receptive fields. But in fact, it turns out that this is not always true. So if we measure the response of the ganglion cell in full daylight or in strong light, it has this center surround receptive field space and also this derivative response in time that I discussed before. But if you move to situations where there's very little light, suddenly the receptive fields change. Okay, so the same cell does not have a center surround receptive field anymore. It just responds to the light in some region. And also in time, it doesn't take a derivative anymore. It just kind of takes an integral of the input over some time scale. So first of all, it's quite remarkable that the retina is able to do this transformation. What it raises questions, mechanistic questions. How does the retina change from using this receptive field to using this receptive field in different light conditions? We won't discuss these questions at all in this course. But the other question is, why does the retina do it? So can you say maybe why in low light intensity it might make sense that the receptive field looks like this? Yeah. Right, but okay, but why? Yeah.
And in a relatively large space, that is the bit of information.
Yeah.
Not contrary when we have a lot of light, a bit of information.
But why? But what? I mean, why? I mean, why? What? Signal to noise. Okay, so again, we need to think about noise. Noise is essential. At low light conditions, I will discuss this in more detail. There's noise in the inputs to the retina. Okay, and once you have noise, so you have a signal, which is the true light, the light intensity, which is related to some object in the visual scene. But on top of that, there is noise. And if there's lots of noise, what you want to do is, as you said, you want to integrate over some time and over space in order to reduce the noise, right? Then if there's spatial correlations, if there are spatial correlations in the visual scene, then we'll still get something sensible about what's going on here by averaging over all these neurons. And on the other hand, the noise will be, the noise goes like, the variance of the noise goes like the number of pixels that you're averaging on. So the standard deviation goes like the square root, whereas the signal goes like the number of pixels. So the signal to noise increases if you average. And so you average both. It makes sense that you average both on space and in time. On the other hand, when there's lots of light, then perhaps the noise is not, so the input noise is not important. And then we want to make use of the redundancies in the image by taking derivatives. Okay? We'll need to encode less information if we're taking the difference between this and this, because they're correlated. Okay, so I'll discuss that. It's a good question, and I'll discuss it in a moment. But before that, just to kind of qualitatively describe what is going on in these receptive fields. So in high light intensity, but this is not open to interpretation. This is fact. In high light intensity, what the cells are doing is they're implementing some kind of spatial and temporal derivative. That determines what they generate as an output. And in low light intensities, they're doing something which is more like an integral. Okay, so what do I mean by noise? So there's one fundamental reason for noise in vision, which you cannot get away with. It exists for physical reasons from quantum mechanics. And this is that what do we observe? We observe a flux of photons falling on our retina, right? Now, the photons have a certain, as I mentioned, flux, number of photons per unit time, per unit area. But the event in which a photon is actually absorbed by a rhodopsin molecule in our photoreceptor and generating a response is a random event. Okay? And it's random for very, very fundamental reasons. This is how the physical world works like. This is quantum mechanics. There's no way to get around it. And therefore, if you ask what is the number of photons absorbed by, say, a photoreceptor per unit time, or in a certain time window, this is a random variable. Okay? And it's distributed as a Poisson variable. So what does that mean? maybe I'll write that down because I'll use that in the next slide. So if there's some flux I, meaning that on average the number of photons falling on a unit area, say time unit. So this will be the flux, and the number of photons falling on some area A on some time delta t will be the average. This will be the average number of photons absorbed in this area over time delta t. Then delta n, because this is a Poisson variable, delta n will be the same as n. Okay, a square root of n. Okay, delta n squared will be n, and therefore delta n will be proportional to square root of n. And therefore, the stronger the light. Now, what determines the number of the flux of photons falling on our eyes? If we have the same visual scene, it's just the light intensity, right? The light is reflected from objects and reaches our eyes. So if we turn if we turn the knob and make the sun 10 times stronger, then we'll have 10 times the photons falling on our eyes. And that's good because it means that we have 10 times, the average increases by a factor of 10. Our retina adapts to it, so it will still generate the same kind of responses, but it has adapted to this. But the noise is now increased by a factor of square root of 3, right? Because the noise relative, if our retina is just dividing the input by the mean, that's the adaptation. So intensity is increased by a factor of 10, but our retina is dividing that, so the signal remains the same, but the noise has decreased by a factor of square root of n over n, which is so 10 times or 100 times more light means that the signal to noise ratio is improved by a factor of 10. The number of this n, the number of photons actually being absorbed. So a Poisson variable, the variance of a Poisson variable is the same as its mean. N is a Poisson variable. N is just what I mean here is n is the variable. This is its mean, and this is its variance, or its standard deviation. This is the standard deviation. So the standard deviation is square root of the mean. Okay. It's okay? I think you're confused about probably something just in the wording, and ask me later if it's not clear. Okay. So now comes some very interesting experiments which were done by Dutch physicists in 1967. Where they looked more carefully about what are the thresholds for perception in our visual system. And the way they did it is that they first adapted our retina to a certain light intensity. Okay, that's I. Okay, and then on top of that, they showed a certain grating, like a periodic stimulus with an intensity delta I, okay? And they just checked for human subjects what is the minimal intensity at which these subjects can see that they're observing it, okay? And so there are many aspects in this graph. I'll go through it very carefully, so you don't need yet to understand it. But what they measured is the ratio between the minimally observable intensity of the stimulus relative to the background. This is what they call M. So this is the y-axis, okay? And this is on the log plot. And in addition, they characterize this as a function of the spatial periodicity of the grating that they're showing. So this is the X plot, okay? Now, what I want to first focus on is not so much the dependence on the spatial frequency, but on the different curves that you see here. So the different curves here corresponds to different background intensity. Okay, so with factors of 10 between each one. So I hope that you can see this. This is 0.0009, 0.009, 0.09, 0.9. I'm not sure what the units are, but there's a factor of 10 in intensity between each one of the curves. And first of all, just looking at it, you see that there's a rich structure here, which is more complicated perhaps than what we would expect. But I want to first focus on these three plots and argue that these are kind of make sense. Why do they make sense? What you see here is that we take a factor of 10. Say, let's go from this one to this one. We take a factor of 100 in the ambient light intensity in I bar, and then what we can discern, the amplitude of a grating that we can observe, increases by a factor of the relative amplitude, right? So this, what is shown here is delta I over I. So when the general light intensity increases by a factor of 100, we can observe a relative amplitude which is better by a factor of 10. You see this, that this is a log plot, so this is a factor of 10. Okay, so a factor of 10 in the light intensity provides a factor of 3 in our signal-to-noise ratio. But that exactly matches what I discussed over there. Because if we have a light intensity which has increased by a factor of 100, then the noise has increased by a factor of 10. The amplitude of the noise has increased by a factor of 10. So to be able to observe some object above the noise, it's enough if the object's intensity has increased by a factor of 10, and therefore its relative intensity relative to the stimulus has improved by a factor of 10. Okay? So again, factor of 100 in the visual stimulus, factor of 100 in the photon flux makes us able to observe an object whose intensity has increased by a factor of 10. Or the relative signal to noise ratio is improved by a factor of 10. So this makes a lot of sense. The fact that these three curves are just shifted relative to each other in this way. But now, as we go to higher light intensity, something happens, right? We would naively expect that as we continue to go to higher and higher light intensity, we will continue to see curves like this just shifted down in this way. And this is not what is going on. The most dramatic thing that you can see is right here. Here we have a certain light intensity and a higher light intensity, and we almost have the same relative thresholds. We're not improving at all anymore. So what this is telling us is that the noise in the input in this region, the noise in the input doesn't play any role anymore in setting what are our perceptual limits, right? So here, everything matches the picture that our perceptual limits are really coming from the input noise, right? Our improvement is exactly in matching with what we would expect. Here, the input noise is decreasing, right, as we go from here to here, but our perceptual thresholds are not improving. So what could be the reason for that? Okay. Okay, so the limit is really not a limit to the intensity that we can see, but the interpretation that we will come up with is that the limit is the limit to the amount of information that our retina can send to the brain. Okay, so there's a signal-to-noise ratio in the input, but there's also a signal-to-noise ratio coming from the fact that there's some limited amount of information. The retina has to somehow discretize or represent the input in a limited way, and by the time we reach these intensities and we try to observe some extremely small perturbation to a very strong light intensity, our retina is not able anymore to convey this information to the brain. The other interesting thing to see is that what happens to the structure of these curves. Now we start to focus on the spatial frequency. So note that at low light intensities, we are best at observing a grating which has a small, low spatial frequency, so something which is very uniform, and we are worse at observing higher spatial frequencies. But when we go to high light intensities, this changes dramatically. We're now best at observing some particular spatial frequencies. We can identify them better than something which is uniform. Does this match something that we discussed already before? Right, that's right. So the change, we discussed the change in the receptive fields of neurons in the retina, and I claim that this is, if they change in that way, that this is what we expect, because if the receptive field is integrating some region, then it's best at identifying something which is uniform over the whole region of integration, because then things add up. And so if the receptive field is just center without center surround, we'd expect to be best at identifying something which is uniform. Whereas if a receptive field is center surround, then such a cell will be most activated by a signal which is varying spatially. And so in this region, it will have the strongest response relative to, and the noise, for the noise, it doesn't matter if you're adding or subtracting.
Assuming that it's the same cell, you can imagine.
This is a good question. So, but I'm just saying that, I'm just saying that we know how the responses of ganglion cells. So look, right, this is human perception. This is human perception. There's a huge gap between what these cells are doing and what we and the subject saying, I saw it or I didn't see it. There are many things happening but if we just...
explanation, like, it's not the receptive fields are changing, at least not in the low level, somewhere in the cortex.
It could be that something is changing in the cortex. Yeah, but okay, so but I'm just saying that if our interpretation is that our limits, our perceptual limits are coming from the retina, it makes sense. It makes sense because, again, if ganglion cells are responsive to something which is varying spatially at a certain characteristic scale, which has to do with the scale of the receptive field, then they will be most responsive in those spatial frequencies, and therefore, in those spatial frequencies, they will have the best signal-to-noise ratio. So this, okay, this is not a proof, but I'm just saying it seems to make sense. But this raises a question: why would okay? So one thing is, if this is the response, the way the retina responds, then perhaps it makes sense that this is how our perceptual thresholds would look like. I didn't prove that. But another question which is raised is why would the retina start to use this kind of encoding, where it's more sensitive to high spatial frequencies, when at high light intensities? And our interpretation, kind of our rough interpretation, was that this allows us, because of the fact that there's correlations between nearby pixels, this may allow us to send more to provide more information about the visual stimulus if we take derivatives relative to taking an integral. And so what we will actually, our main goal in the next few weeks will be to understand whether that's true. And in fact, sometime after this work was done, quite a lot of time after this work was done, Attic and Redlich, in a very, very important series of papers, explained the perceptual thresholds, the structure of receptive fields and the perceptual thresholds of vision based on the notion of maximizing mutual information. So they had some, I will not explain too much what you see here, but these plots are essentially the same as the ones that you've seen before, just inverting. I took this from their paper, so they plotted it a little bit differently, but it's the same, essentially the same plots that inverted in the vertical direction. And their assumptions, they made several assumptions. One was indeed that our perceptual thresholds are coming from the retina and not from anything else in processing in the brain, and that the goal of encoding of the retina is to maximize information about the visual stimulus while making some simple assumptions about the statistics of visual stimuli, which we will discuss later on. So they take some assumptions about the natural statistics of visual stimuli. They come up with some theory for maximizing information by the retina, and as we will see later on in the course, this theory predicts both that the structure of receptive fields should change as we go from low light intensities to high light intensities in a way that matches the physiology. And if you use that to ask what would be the perceptual threshold of subject based on at different light conditions, you come up with curves that look like this, and in fact the lines are coming from the theory, the symbols are coming from the experiments that I shown you previously. So the fit is remarkable, although of course there are some parameters in the theory, so that's something to keep in mind. But nevertheless, the theory, at least with tuning of a fairly small number of parameters, can explain this whole rich phenomenology. Okay? Good. So that's what I wanted to tell you in this in the slides. And now we go back to the whiteboard. And as you'll see, I mean, the math will sometimes be a bit complicated, and for some of us that by itself will be fun. For some of us that will not be so much fun. But the real fun, I think, and the reward is in understanding something about how the visual system works. Okay, I will just start by formulating a general framework that we will be using for some time, and I will steal a few more minutes because I started a bit late. Okay, this is okay. So we now want to discuss the problem of encoding of a stimulus when we have multiple inputs. And multiple outputs. And I'll formulate this as a fairly general problem, and we'll go back to vision later on. Well, first we'll think about it quite generally. So imagine that we have some input units, and we have some output units, and we'll have n input units and n output units. So the inputs, we will call them x. And this will be a vector x1 up to xn, and m outputs, we'll call this vector y, y1 to ym. Okay, so we have here n, here m. And we will not consider now nonlinearities when we discuss the single transformation. We'll discuss nonlinearities, but here we will be even more simple-minded and just think about linear transformations, which kind of makes sense because, as I remind you, receptive fields that characterize well responses in the retina and even in V1 for some neurons are characterized in terms of a linear summation of inputs. So this particular neuron will just sum up inputs with some weights, and another neuron will sum up the inputs with some other weights, right? And so these weights, we will call them Wij. So first of all, one thing that I mentioned is that possibly, I didn't mention is that possibly M is smaller than N. When we discuss the retina, we will want to consider a convergence. And the weight, if this is Ij, this is Ij, this is what I will call Wij, okay? Weights, Wij. And some conventions. So one just convention to maybe I'll do that, and then I'll end for today. Just the convention that I use is that, as you see here, these vectors are going to be column vectors. Their transpose is therefore a row vector. And I want to mention another, so for example, if we take something like X transpose times X, this is like a row vector multiplied by a column vector, right? So this is just, what?
The norm squared.
Yeah. That's just the sum over Ixi squared, and that's a scalar, right? That's a number. But I will also use another notation where I will write something like X times X transpose sometimes. So this is a column, and next to it a row. And what I will mean by that is that this is a matrix. X has dimensions n. This is going to be an n by n matrix. And by definition, this is just definition, X transpose Ij is Xi Xj. Okay, so this is a matrix whose entries in the Ij place is the Xi times Xj. And you will see later why we need this convention. And you know what, I'll just say one more thing, and this is that I'm going to assume now something about the statistics of the inputs. I'll assume that there are Gaussians, multidimensional Gaussians, so jointly Gaussian. I'll assume that they have zero mean just for simplicity. Of course, inputs, I don't know, to the light, to the retina don't have zero mean, but let's just subtract the mean. And therefore, I can write the probability distribution of the input as a multidimensional Gaussian. So this is a general form for a multidimensional Gaussian. You went through this with Netta. What we mean by this? This is a sum over I and j minus half a sum over I and j xi c to the minus 1 ij xj. This is the inverse of the matrix C that appears here. And you know that what characterizes this Gaussian is that the covariance of if this is for a set of vectors that are distributed according to this probability distribution, the covariance is Cij. So the matrix that here appears as an inverse of a matrix. The matrix C is really the covariance matrix in this of these variables. And another way to write this, just using the notation that I introduced, is that the matrix C is the average of the matrix X transpose. Okay, so we are going to assume that inputs are jointly Gaussian. I'll discuss next week why, not next week, but on Thursday. And we'll add also some assumptions on noise, and then we'll formulate a problem of optimization.
מה זה אומר? זה אומר שהשינויים ב-N ביחד לממוצע שלו, זה הדלתא N. זה פשוט סימון. לא עשינו עבודה בפיזיקה. בניסויים הרבה פעמים מקובל לרשום את המשתנה, וברגע רשמתי לו את השקיעה במשתנה, בתור, יש מקרה שאנחנו כותבים N, ואת השקיעה כותבים בתור דלתא. השקיעה זה כאילו הסטנדרט deviation. פה בסימון הזה.
שכחת את הישיבות, שכחת את
זה ממש פשוט ברגע שתוריד אותי.
ברגע שאתה יודע את הפתרון...
לא, תראה, אתה תראה את זה, סליחה, זה להציב את ההגדרה, ישר הופך משתנה, זה הכי קשה. זה היה לי